Hello, I'm going to talk about cat today, and I'm going to talk about how I'm going through it, and then I'm going to talk about my syntax and all of that stuff. This video is probably going to be a little longer just because this is obviously like a more complex topic. So unlike traditional linear testing where all the respondents receive the same set of items, the main purpose of computer adaptive testing is to perform iterative and adaptive administration of the items. This helps determine a more accurate estimate of theta, which is the ability level. The items are selected and administered one by one, and the selection of the next item is conditional upon the administration of the previous item and their responses, and the provisional estimate of ability level. CAT has several advantages with respect to linear testing, and among others, it requires less items to reach the same level of precision for ability estimation, leading thus to shorter tests for the respondents. And ability estimates are available directly after the test administration for immediate feedback to test takers. So obviously there are a lot of advantages to using CAT. Any CAT process requires a calibrated item bank and can be split into 4 steps. The first step is the initial step and consists of selecting one or several appropriate items as the first items. The second step is the test step, and this is where the items are successively chosen from the bank and the ability level is re-estimated after each item administration. This is done several times until it basically hones in on the best estimate of the ability level for the respondent. And then that's when the third step happens, which is the stopping step. This is where you set the parameters for the stopping rules of the CAT. And then the final step is going to yield that final estimation of theta, and you can also get other information. So about the package CAT-R, it offers a variety of options to generate response patterns in a CAT environment. It provides first a pre-calibrated item bank, and then by selecting all options related to CAT assessments, such as add interim and final ability estimators, a method for next item selection, and a stopping rule. So these are the types of parameters that you can put into the CAT syntax. CAT-R is very flexible, it's easy to update, and several of its components can be used even outside the CAT framework. So you can actually get the ability estimation and related standard error computation routines. Though basically developed as a working routine for CAT studies, you can also actually apply it. So you can use CAT-R for real CAT assessment platforms. It doesn't just have to be for research, which is pretty cool. So I'm going to briefly describe the specification of polytomous, hopefully I'm saying that right, I think I am, IRT models, which we talked about in class. And that's what I'm going to be doing here just because it was the example that I best understood and was able to get to run on R. So I'm going to talk a little bit about that since we're used to talking about 1, 2, and 3 PL models. So the specification of a polytomous IRT model is composed of 2 elements: an appropriately defined matrix of item parameters and the new argument model added to almost all existing functions. So that was with the update of the CAT-R package. By default, model takes the null value and refers to dichotomous models, for which the item bank format is left unchanged from previous versions of CAT-R. So in previous versions of CAT-R, you could use the item bank or create item bank function within the package. However, in 2017, they updated the CAT-R package, and they actually took that away and replaced it with gen polymatrix function or gen dichomatrix function. So the basic steps that I'm going to be using to code or generate the CAT patterns in R are as follows. 1. An item bank of 500 items is going to be randomly generated with PCM as the IRT model. Moreover, each item has between 2 and 5 response categories. Each cat starts by selecting from the item bank the item that is most informative for the true ability level of 0. This is similar to what we talked about in class. So whenever the person walks in, you're assuming an ability level of 0, just because that's the best estimate that we have at that point before they complete the cat. So this means, among others, that each cat will start with the same item. This restriction can nevertheless be relaxed by using another approach. The current one, however, is most commonly used in real cat assessments. Ad interim ability is estimated with the maximum posteriori, or Bayes modal method, with the standard normal prior distribution of ability. 4. The next item to administer is selected by making use of the Kullback-Leibler, or KL, divergency criterion. The stopping rule is set as a precision criterion. Adaptive administration ends when the standard error of the ad interim ability estimate becomes smaller than 0.3, which you can change. You can customize that. The final ability estimator is the traditional maximum likelihood, or ML estimator. And then this example is not going to contain any option for item exposure control, so I'm just going to follow through with the example that I found. So first, the package cat R must be loaded from the library. Cat R is going to provide routines for the generation of response patterns under unidimensional dichotomous and polytomous computerized adaptive testing framework. It holds many standard functions to estimate ability, select the first items to administer, and optimally select the next item, as well as several stopping rules. So the first step is the item bank. This is the central tool for adaptive tests, and an item bank is a collection of items that can be administered to the examinees. In order to generate response patterns, it's sufficient to have access to the item parameter values. In this framework, the item bank is assumed to be calibrated prior to the start of the cat process. An item bank of 500 items is randomly generated here with the PCM as the IRT model. Moreover, each item has between 2 and 5 response categories, as I mentioned earlier. In the syntax, bank equals the name of the object of item bank that we're creating. The gen polymatrix command is used for item bank generation for polytomous models. The items is the number of items to generate. The default is 100. The model is the type of IRT model that you want R to run. And then nrcat is the maximum number of response categories to generate the default, or to generate the default is 3. PCM is the partial credit model, which is a version of a polytomous IRT model. So in summary, this is going to create the item bank. So in order to start any cat process, you have to select at least one item in the item bank and administer it to the examinee. This is just like we talked about in class. So a single item is going to be selected at this step, and in the absence of any prior information about the examinee's ability level, you fix this ability level equal to the prior mean ability value. This is usually 0. With this prior belief, the initial item is selected as the most informative in the item bank for this ability value. So once again, it's going to start by selecting from the item bank, more specifically the one that is the most informative for the true ability level of 0. So each cat is going to start with the same item. This is the approach that's used in actual cat assessments. And the line of code that I'm going to run creates a starting list using the list function with the assumption that theta is 0 and that there is one item. So theta within the code equals provisional ability estimates, and in our items is going to set the number of starting items. Okay? So this is the test step. Once the initial items have been administered, you can get a first provisional estimate of ability by using the current set of responses. This step can be described as follows. First, estimate the ability level by using the currently available information, which is the previous response pattern to which is added the latest administered items. And this is going to be set as the provisional ability estimate. The second part is selecting the next item among the bank items that have not been administered yet, according to the provisional ability estimate and the method for the next item selection. Third, administer the selected item to the examinee and update the response pattern. And fourth is repeat steps 1, 2, 3 until the stopping criterion is satisfied. So any kind of ability estimator can be considered for the test step, but the ML estimator that I mentioned earlier is often avoided because it often returns infinite estimates at the early steps of the CAT process. The BM estimator with a prior normal distribution is a common choice for this step. So the next item to administer is selected by making use of the Kullback-Leibler or KL divergency criterion that I mentioned earlier. This is used as a rule for selecting the next item in the CAT process. You can use this for dichotomous or polytomous IRT models. Within the syntax, test is the name of the object that I'm making. List is a list of arguments to be tested. And then within that list, I have item select, which is going to specify the item selection rule, which is KL, like I mentioned. BM is going to specify the Bayes modal as the estimator, and the KL is going to return the value of the Kullback-Leibler for the specified item bank, and then method is the ability estimator where you would put BM. Okay. Next, we move on to the stopping step. So any CAT process stops when the stopping criterion is fulfilled. The precision criterion, which is what I'm using here, forces the CAT process to stop as soon as the precision of the provisional ability estimate, that's what I'm using here, sorry, that's what I meant, reaches the pre-specified level of precision. So typically the precision is measured by the standard error of the ability estimate. The lower the standard error, the better the precision is going to be, because this is going to mean that you're closing in or honing in on that ability using a 95% confidence interval, so you want that to be smaller. Thus, you usually fix a standard error as a threshold value, and then the items are iteratively administered until the standard error of theta gets smaller than or equal to that threshold. So that's how it's going to know to stop. So within the syntax, the stopping rule is going to be set as a precision criterion. And we want the add interim, or the standard error of the add interim ability estimate to become smaller than 0.3. So in the syntax, stop is going to set the stopping rule, and I'm going to put that into an object called stop. And then rule is a vector with the names of the stopping rules specified. Precision specifies that THR is the precision level or standard error to be reached before stopping. So 0.3 is the theta, or the standard error of the ability estimate. Okay? The final step of the process provides the final estimation of the examinee's ability level using the full response pattern to the adaptive test. The final ability estimator here is the traditional maximum likelihood estimator. And within the syntax, final is what I'm naming my object. List function is used to specify maximum likelihood as the method, which is, once again, the ability estimator. And then ML, it stands for maximum likelihood within that syntax. Okay, you can look at the first rows of the generated item bank stored into the object that we made called bank with the head function. and you just specify the object as bank that we created earlier. So here are those first few lines. According to the PCM parametrization, items 1 and 2 hold 4 response categories. Items 3, 4, and 6 have 5, and item 5 has only 3. So the 4 steps of the cat process are now plugged in the random cat function as given below, what I'm going to go into next. For the particular simulation, one examinee with true ability level equal to 1 is what we're looking at, and it's expected that they're going to be classified as having an ability level is lower than 2 with a rather short adaptive test. So here a single cat pattern will be generated from the usual random response generation process with a true ability level of 1 and all aforementioned cat options that I created earlier. So the corresponding R code is REG, which is the name of the object that I'm creating. Random cat is the function for random generation of adaptive tests for dichotomous or polytomous models. It generates a response pattern to the test for the given item bank. Cat parameters are specified within the parentheses here. We have true theta, which is the estimate of the true ability level of the examinee. The item bank, you can specify the correct object bank from what we made earlier. The item bank contains the necessary item parameters that are needed to run the cat. Model, we're specifying the polytomous model to be applied. Start is an option for starting the adaptive test specified by the object start that we made earlier. And then we have basically the same idea for stop and final. So stop is the stopping rule. Test is the list with options for provisional ability estimation and next item selection. And then final is a list with options for final ability estimation. Okay, so in order to view that output, we use the print function. And here we have an output. A lot of it is what we put into the model. So the structure of an output from the random cat function is a list of class cat with many different arguments. Basically, the function returns the final results. You have final ability estimation, standard error, and confidence intervals, and then also the complete response pattern and the matrix of item parameters of selected items are also returned. So for completeness, the vectors of provisional ability estimates and standard errors are displayed so that one can plot the curve of ability estimation through the cat process. Finally, all input arguments of the start, test, stop, and final list are returned within the cat output, which we can see here. The first part of the output is a summary of the different settings of the test step. The true ability level is mentioned first, which is 1. Followed by the parameters for the initial step, the test step, and the stopping rule. There is no control of item exposure here. Usually it would be described, and currently only the randomesc method is available. But for the example that I'm doing, only one optimal item is selected. So there's, you can see that in the output. And you can also see that there was no control for content balancing. The details of the adaptive test are then returned. So that's where we are here. It consists in a matrix with 1 column per administered item and 5 rows with respectively the item number of administration, the item identification number, so this is how it's listed in the item bank, the generated response to this item, the provisional ability estimate, and its standard error. Okay, so here we have number of item administration. So we have 1, 2, 3, 4, 5, 6. the item identification number here, the generated response pattern here, the estimate of ability is here. So as you can see, once you get past 6, which I'll explain in a minute, you can see that CAT required only 6 item responses to reach the pre-specified level of precision in the ability estimation process. And then it ends with the output ends with the results of the final step, the final ability estimator, final estimate, and standard error, final confidence interval, and the final conclusion with respect to the classification rule. So again, this CAT required only 6 item responses to reach the ability to reach the pre-specified level of precision that we put into our syntax earlier. So the final standard error is listed and is larger than the requested threshold, which was 0.3. And then, that's due to a change in the ability estimator between the test and final steps. So the final ability estimate equals 1.047 or 0.283, which is not far from the true underlying ability level of 1. So the last thing that I'm going to do is the plot function, which is going to permit a visual representation of the CAT process by plotting the provisional ability levels against the test length. Okay, so here we have that plot. This basically plots the results of the CAT simulation. So this is basically a plot of the output that I just ran through. The classification threshold is displayed by the horizontal dashed line here. And then the true ability level is indicated by a solid horizontal line here. So we see that 1 is the true ability level. So as the number of items increases, the standard error of ability estimate decreases. As the amount of available information from people responding becomes larger as the test continues on and people respond to items. So this is telling us that after 6 items, the ability estimate is close to 1, the true ability level, and the standard error is small. So as the test goes on, the available information increases and the provisional standard errors of the ability estimates decrease accordingly. This is how it figures out where to stop and how to get the best idea of theta. Consequently, narrower confidence intervals are obtained. So after the 6th item administration, the confidence interval does not contain the threshold value 2 anymore, which forces the CAT process to stop. This is obviously in agreement with the R output above, but is again visually displayed in this plot. So note also that the ability estimates are getting closer to the true level of 1 as the items are being administered. So here's where we capture that. That's pretty much all that I have for CAT, and over.